Have fun picking up your foster children, Jack.
All right. On the graph, on the back side on number 8. Okay? So here's the deal. Well, I got the party started like this. Okay? So this is that initial explosion where you have this massive acceleration on these really steep lines. Okay? And notice that I gave you a whole bunch of line out there. Okay? I don't want this. Okay? No. The tree is dead. Have it not died in vain. All right? So let me give you a hint. The top line is going to go something like this. Okay? That's what the top line is going to look like. Because the cart's rolling uphill, it's going to slow down, and then it's going to speed back up. Okay, it's going to change direction. Now, what you have to decide is what's going to happen on the bottom cart. Is it going to be, you have 3 options. Is it going to be kind of flattish? Is it going to be parallel with that top line? Or is it going to be more steep? Okay? So that's the decision that you have to make. And I'm not going to guess which one I think it is. Okay? So if you want that parallel, you take a ruler and you draw those lines completely parallel. If you think this thing is more shallow, you draw it more shallow. If you think it's steeper than that line, you draw it more steep. Okay? Got that. Everybody cool? All right. Now, let's talk about the questions. So, if your answer to 2A is wrong, everything else is going to be wrong, okay? So your answer to 2A should be in the mid-700s, okay? Because if that is wrong, literally everything that you're going to do from the rest of that problem is going to be wrong, okay? But keep in mind, are you talking about, pay attention, is the question asking about momentum, or is the question asking about change in momentum? Okay, they're related, but they're 2 sides of a coin, okay? They're not the same thing, so pay attention to that. On number 3, and this is a completely idealized situation. So here's Tony. He's carrying the football. He has Dane Bramage, because he don't always wear a helmet. And then here's the 2 linebackers, Bubba and Leroy. Okay, and this is taking out like cleats and pushing and all of this good stuff. So this is a purely idealized momentum situation. Okay, so don't get hung up like, what if they have better cleats? I'm happy for them. Not part of the equation. Okay. This is just the momentum part of this, okay? So, mags, because they're in opposite directions, what do you know about their velocities?
The opposite.
Yeah, you have to choose a side. Make one of them positive, make one of them negative, okay? I don't care which one you do, pick one, make one positive, make one negative. So here's the basic idea. If you let Tony's momentum be a positive value, and the overall momentum is positive, Tony scores. If you set that positive, and then your overall velocity ends up being negative, he gets pushed back. If everything adds up to equal to 0, you just stop right at the goal line. Okay? So, keep in mind, this is a California problem. All right? I think I put like they become entangled in a mass of testosterone or something like that, something clever. So because it's a California problem, what can you do on the right side?
Add the masses together.
Add the masses and factor out that velocity, okay? So if you do 3 right, that overall velocity is a really small number, okay? It's a really small number. Now, let's talk about question number 4. Because if 4A is wrong, everything is going to be wrong. Okay? So your answer to 4A should be like 1.8 meters per second. Okay? Because if that is wrong, everything is gonna be wrong from there on out. Huh?
What number did you say?
4A, 1.80 meters per second. Okay.
The whole life's ruined.
Now, here's the whole thing that I want you to see as you go through this. First off, pay attention to F, okay? When I say that it's gonna, the ball's gonna come in, now it's gonna get hit with like a rubber bullet. So this is what I tried to show you the other day. So that rubber ball is gonna come in, it's gonna hit the block, and it's gonna bounce back. So did the velocity change direction? Yes, so what happens when something changes direction in terms of sign? Sign changes. Keep that in mind, okay? Keep that in mind. So obviously, some of your answers on number 4 should be negative values. If you have no negative values on number 4, you have done something horribly wrong. Okay? Thanks.
I have a question for 2D.
To what?
D.
Okay?
I was curious if it was around like 100,000 or around 700.
Around 700.
Okay.
Yeah, what you should see on number 2 is that you should get a lot of the same answers, but just different signs. Because they hit and they stop. So their momentums have to be equal and opposite. Got it? Okay. Anything else? Going once? Going twice? So, get that hand.
Oh, in my back.
Don't mind the bike taking up the corner on mine. I don't know.
Whose turn is
You
it?
do too. Don't lie.
I'll do it.
You're not even wearing the cool shoes to lie, man.
Oh wait, whose homework?
Do I have to get like tested for rabies?
What's the vocab test?
Glad to see you guys aren't matching today. That'd be.
I'd like to do that.
I'm sure he could pull it off. Don't get me wrong.
Oh my
But-
gosh, we should do, can we, was it?
No,
What?
no.
Oh.
What was the question?
Huh?
The way middle stick.
I was just gonna be like, for Stuco, for homecoming, we should have the competition where you guess your type or whatever.
We're doing that next year.
Yeah, but don't call it gender bender day, because that's not politically correct.
Oh, no.
That's what it's usually called at other schools, but maybe don't say that. Yeah, so you dress as the opposite gender, maybe.
Or the same.
Or the same gender. Just depends on your type.
What are you talking about?
Because I was gonna say, usually it would be you dress as the opposite gender, but you know, that wouldn't be really inclusive, so.
Huh? That look better. There was 2 papers in a row you did that.
Honors physics test next Wednesday. We do?
Wednesday? I thought it was Thursday.
We lied.
AP rig?
Test.
I think register.
Oh.
So that means, do we want the bio test on Friday or Tuesday?
Friday.
Tuesday we have a gov test.
So Friday.
Not that they're easy rolling. He gives you the answers.
He does not. I'm always, okay, the FRQ is easy, but like the other part isn't.
You said he would review with the test.
Oh, it's horrible.
Are all the papers the same?
A ball with a massive. Do we have the same one?
Yes.
Who threw this? No, I didn't.
You all have the same.
Who threw that?
It came from that direction.
How long did this assignment take you again?
Oh yeah, how long does that take?
2 hours. Well, it depends on like if you actually watch or if you just like bullshit.
The news one? What did you do?
Probably like an hour.
What did you do?
I watched them.
Watched it?
Oh, I like the little
Paper.
All right, thanks. Come on, let's go.
What are
How's
we
your
doing?
signing, by the way?
You said start the camera.
It's already started.
Oh, it is?
Yeah,
All right, so here's the schedule for today
I guess
and life in general
I'm not a person.
for the next however many days. So today we're gonna finish up linear momentum with this big complex problem involving the drop ball, okay? Then we've got a video to watch on car crashes, so you won't have any homework tonight, okay? Then we'll do angular motion tomorrow. We'll do angular momentum on Monday. We'll review on Tuesday and then have the test on momentum on Wednesday, okay? Then Thursday, we will start work, literally, we'll start as work.
Starting work on Thursday?
Literally, we're starting.
Is that the one with like
That's
fish?
the
Oh,
topic
like,
is
know how much
work.
work.
Is it called fish or something?
No, that's angular motion. Well, that's gonna be Tuesday.
Oh,
Or, excuse
okay.
me, Monday is gonna be fish day.
Because they did not stop talking about fish when I was retaking my test yesterday.
Yeah. Yeah, we'll hit fish.
How long do you have to
tomorrow,
stay here for them?
What is fish?
Don't worry about it.
Monday. We'll figure it out.
You'll probably hear it when you take it.
Do we get an actual fish?
No.
Oh.
It's not
And
actual
then-
fish.
Friday, a week from tomorrow, is what we call Africa Day. And it's just kind of become the tradition, the Friday before Thanksgiving, is that we kind of celebrate, all make my ranch scrambled eggs. That's a whole other story.
What?
If you want to bring in any food, we'll kind of partake. And then I'll show you footage of me when I was young and thin. And,
You're stupid.
no, I'm not. No, I'm not. I appreciate that, but that's so yeah, so when you see the footage of me in Africa, here's what everybody says. Let's just get this out of the way right now. You were so young and thin.
Wow.
Yeah.
You're
So over the years, my glasses have gotten smaller, my waist has gotten bigger. So that's kind of been the transition. So anyway, so this problem that we're gonna work, okay? We're gonna work this thing start to finish. I wanna make sure everybody knows exactly how to do this problem. Because I promise you, on the test next Wednesday, you are going to have a problem just like this. Except the only thing I'm gonna do is I'm gonna change the numbers, okay? So I wanna make sure everybody's cool with how this works, because it ties in a whole bunch of different things. Kinematics, momentum, forces, graphing, acceleration, the whole smash, okay? So this is why I want to spend today kind of going over this problem. Also, clothing orders, okay? If you want to order any merch, or if you have some friends of yours that you think might want to order some, okay? I don't necessarily need the money tomorrow, but I need the order because I've got to get that in, okay? So if that's something that you want to do, then, like I said, it's like, I don't have the money, just give me the order. We'll worry about the money later, okay? So if you're gonna order something, there's that. Okay, so here's the setup on this problem. So we got a ball up here, we're gonna drop it, boom, it's gonna hit, it's gonna bounce back up. So what we're ultimately gonna find is what's gonna happen in terms of the change in momentum and the forces when that ball is in contact with the ground, okay? So the big picture is that we need a whole bunch of things. We need how fast the ball is going when it hits the ground. We need how fast it's going when it leaves the ground. We need how much time it's in contact with it, and then we can calculate everything from there. So this is where this kind of goes old school, because you've got to tie in a whole bunch of different things. So if you look at this problem, so let's kind of set this up. So the ball is going to come down, it's going to hit the ground, boom, it's going to bounce back up. So if you look on the problem, you're dropping this thing from a height of 1.85 meters. It's going to bounce up to a height of 1 meter, and I give you the time that it's in contact with the ground. So before we start any calculations, okay, before we start a single calculation, let's make sure everybody's cool with the parameters. Anything going down is negative, whether that's velocity, acceleration, force, displacement. Anything going up is going to be positive, okay? Same thing, acceleration, whatever. Okay. So let's start with the velocity time graph. So where's my velocity time graph going to start? Do not make this
Zero,
difficult.
because you're dropping it, right?
Yeah, I'm just dropping it. What's the initial velocity?
0.
0, okay? So what's it going to do from there? It's gonna speed up. Is the line gonna slope up or is the line gonna slope down? Down. Why?
Just negative.
And we're defining down as being
Negative.
negative. So I want to let go of this ball, boom, it's immediately going to begin to speed up. So what's going to be the value of the slope of that line?
Negative 9.8.
Yeah, okay, hey, kind of heard that number before, right? So here's what's going to be important. What's going to be the sign of the velocity when it hits the ground? Negative, because when this thing hits the ground, it's going to have some big negative velocity that's going to be pointing down. So when this ball hits the ground, it's going to have, come on, some big negative velocity vector, okay? Now, as soon as it comes in contact with the ground, what's it going to start to do? Speed up or slow down?
Slow down.
Slow down. Rapidly or slowly?
Rapidly.
Rapidly. Is the ball going to accelerate when it comes in contact with the ground?
Yes.
Yes, but that acceleration is going to make it speed up or slow down?
Slow down.
Slow down. So it's initially going to slow down. So on an atomic level, when that hits, we're taking what we call kinetic energy, which is going to be the next big unit. Kinetic energy is the energy of motion. So what it's doing is it's taking the kinetic energy of motion and it's storing it in the distortion of the golf ball. Okay, so we're going to compress these particles that make up the golf ball. Mother Nature doesn't like that. Mother Nature goes, cool, okay, I'm going to push you back up. So as soon as this ball hits the ground, so this is when it hits the ground. That point in time, right there, hits the ground. So what's that graph going to do at that point?
Go back up.
Well, I can't go straight up because that becomes undefined. But it's going to be really, really steep, right?
Yeah.
Okay. Why do you know it's going to be really steep? Yeah. Okay. Boom. When that contact, when it's in contact with the ground, that isn't very long. It isn't like I catch it and slow it down and then throw it back up. Okay. That would look completely different than just pink. Okay. So this line is going to come up like this. So when it hits, okay, let's talk about this. When it hits, what do you know about the velocity? Is it going to be positive or negative?
Negative.
So it's going to hit with some negative velocity. Okay? It's going to be some negative number, right? We'll deal with that later. I don't know what the number is. I don't care what the number is. We'll get to that point. So here I've got initially negative velocity, negative acceleration. I'm speeding up. Bam! Hits the floor. Now what becomes the sign of my acceleration? Dime. Positive. So now I've got this big positive acceleration with negative velocity, and that's going to make it do what? Speed up or slow down? Slow down. So at this point, we are slowing down. And we are slowing down rapidly because we're taking that kinetic energy of motion and changing it into the potential energy stored in the spring. Now, what would this graph look like? I'm not going to do this for any number of reasons. But what would that graph look like if that was a raw egg?
Stop at 0.
At this point, what's it going to do?
So,
Flat line. It's just going to stay right there, right? Raw eggs don't have much balance, okay? I don't recommend that you try that, but if you don't want to, okay? Try it at home, not in my room. So if that was a raw egg, right there, sit, stop. But is that what happens? No. What does it do? It begins, so what happens is that if you could look at this like in slow motion, the ball is going to hit, the ball is going to get distorted because we're taking that kinetic energy and we're storing it as potential energy. So when you have maximum compression, that's when that ball is completely stopped. Then Mother Nature goes, not digging it, so Mother Nature is going to push that back up. Y'all have done a similar type situation. Remember back when we started, we were doing velocity and acceleration. Y'all pushed the cart into the wall and the spring hit, and then it bounced back, okay? It's the same idea of what's happening here. Instead of using a spring, we're using the molecules that make up the golf ball that don't like to be compressed, so they go, hey, screw you, I'm gonna push back against this and rage against the machine. So you store energy here and then it pushes back up. So at this point, that's when you have maximum compression of the golf ball, okay? All those particles are compressed as far as they're gonna go. And they're going, not digging it, nope, 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 nope. We're gonna push this thing back up. So when that ball begins to go back up during that transition, so this right here, the velocity is 0. That's when it stopped at the ground. That's when you have maximum compression. So what's the graph gonna do next? Keep going up, okay? So it's gonna cross over like this, okay? But now what's it doing? Now it's slowing down or speeding up?
Speeding up.
Speeding up. I can't go much slower than 0, okay? So we stopped, we fully compressed it, and now we're going to speed up. Oh, right, because now what's the sign of my acceleration? Positive. What's the sign of my velocity?
Positive.
Now I'm going to speed up, okay? Now, at this point, the ball is going to leave the ground. Fly, be free. See ya. It's out of here, right? So at that point, the ball is going to leave the ground. When it leaves the ground, is the velocity of the ball a positive or negative number? Michael, when the ball leaves the ground, is the velocity a positive or negative number?
When it leaves the ground, it's gonna be positive.
Why? You're right. Which direction is it going?
Because it's going up.
Well, how do we define up?
Positive.
Positive. So at this point, that's when this thing is going to leave the ground. Now, let's think about this for just 1 second. Michael just correctly stated that when it leaves the ground, it's going to have a positive velocity. So initially, my velocity vectors were negative and getting bigger, right? It hits the ground very rapidly. The velocity vectors go to 0. Then the velocity vectors switch sign and they get big really fast. Okay, and that's when that material is expanding. It's going to leave the ground. It's going to bounce up. So here's my question. Okay, the ball is going to bounce up to a height of 1 meter. We started at 1.85, but it's going to bounce to a height of 1 meter. So I want you to think through this very carefully. Is the positive velocity when it leaves bigger or smaller than the negative velocity it had at impact? So is the positive velocity going up a bigger or smaller number? And don't get hung up on negatives and number lines. This is not a math class, okay? I'm just talking like absolute value. So when it leaves the ground, is that velocity a bigger or smaller number than when it hit?
Smaller.
Why smaller? Gravity was acting against it when it fell.
Yeah, but.
How do you know it lost energy to the
Because it
ground?
doesn't go as high on the way.
Oh, it doesn't go as high.
Oh.
Now, what if it left the ground with the same velocity that it hit with? It would bounce back up to the exact same height, right? It would bounce back up to the exact same height, which would be the ultimate physics demo to do. If I had the magic bouncing ball, I could drop that, I could walk away, and that ball would bounce back up to the same height every time. It'd be the ultimate demo to do. Okay, you all would not pay any attention to me because you all would be captivated by the bouncing ball. It just keeps going and going and going. Okay, right? Worse yet, what if I drop it really low and then over a period of time the ball started bouncing higher? Okay, that would be cool to watch. Okay, all of our energy problems would be solved, by the way. Okay, it's like what? How did you fix the energy crisis? We dropped golf balls, they just started bouncing higher and higher and higher. Cool, okay, cool. Not gonna happen. So here's what you know, and again, keep in mind the big picture. Here's what you know. The positive velocity it has when it leaves is less than the negative velocity it has when it hit. Okay, so we don't know the numbers yet. I don't care what the numbers are. We'll deal with the numbers later. So when it leaves the ground, right here, that's going to be a positive velocity, but it's going to be less than the velocity that it hit with. Okay? I realize this is getting fairly jumbled, but at this point it leaves the ground. So what's this graph going to do once it leaves the ground?
So now go towards 0.
It's going to go to 0. At what rate?
Negative 9.8.
Oh, so will this line here be parallel with this line here?
Yeah.
Yes, because they're going to share the same acceleration. Because gravity is making it slow down. So then you're going to have something like this. So that's also negative 9.8 meters per second squared. So let me redraw this a little bit cleaner, okay? So here's your velocity time graph. Doink. This is when it hits. So it's going to hit with some negative velocity. This is when it's going to leave. And that's going to be some positive velocity that's less than that negative velocity. And then it's going to go like this. So this segment and this segment both have a slope of negative 9.8 meters per second squared. So when is the ball speeding up? So you have 4 distinct regions. 1, 2, 3, 4. And how many regions is the ball speeding up? 1, 2, 3, or 4?
1.
1?
Yeah.
2.
This is like an auction. Initially, we had a bid of 1, now we hear a bid of 2. Do I hear a bid of 3?
It's 2. At least 2.
Morella, are you bidding 3?
It's 3.
It's 3.
Yeah.
Okay? Anybody go 4?
No.
Oh, wait,
Thank
wait.
God. It's like, oh, it's speeding up the entire time. Let's think this through. Okay, so does everybody agree that it's speeding up in this region?
Yeah.
You have negative velocity and negative acceleration, you are speeding up. Okay, it's falling, it's speeding up. Okay, so we're increasing the velocity here. True?
True.
Boom, it hits the ground. What does it do?
Slow down.
Slows down. Storing that potential energy, that kinetic energy as potential energy. What's it doing from here to here? Speeding up. Why? How do you know? Positive velocity with,
Positive.
or the ball is going away, or the line's going away from 0 meters per second. So here you are speeding up. Once it leaves the ground, what's it going to do?
Slow down.
Speed up like that? Oh no, slow down.
No, because it's going towards
Yeah, you're right. I'm just sorry. No.
It's okay.
So how many regions is it slowing down?
2.
2. How many regions is it speeding up? 2. Okay? Got the idea. You have the big picture. Now let's start to do some math. So on the way down, what's my initial velocity?
Negative 9.8.
0. I dropped the ball.
Xenon's
No. V naught's going to be 0 meters per second, right?
C.
What's my acceleration, Cooper?
Negative 9.8.
Okay, I know my acceleration, thank God. Now, look at how I'm defining this problem. The ground is defined as 0, okay? So, is my initial position positive 1.85 or negative 1.85? Positive 1.85. What's the final position of the ball on the way down?
0.
0, because it hits the reference point, right?
Right.
Okay? So what am I trying to find?
Changing momentum.
No.
Oh, sorry.
No. That's the big picture.
Oh, okay.
I got to take baby steps. What do I have to figure out if I'm going to calculate the change in momentum? What do I have to have? I got to have 2 velocities, right? I have the velocity when it hits and the velocity when it leaves. So I need to find another velocity. So I don't have time, nor do I care about time. Do not use the time that I gave you. That's how long it's in contact with the earth, okay? That is not how long this thing has fallen, okay? So I don't have time. So Preston, what am I going to do if I don't have time?
I'm gonna do that equation.
That equation. So you're going to have v squared, that was horrible, v squared equals v naught squared plus 2ad. True?
True.
So what are you solving for? The initial velocity to the final velocity?
Final.
Final. So now v is going to equal the square root of v naught squared plus 2ad. Now, what I'm about to do is wrong, okay? Do not do what I'm about to do, okay? It's wrong. And you're going, why are you doing it? Because this is what you all are going to do. So, oh, v naught squared, that's 0 plus 2. I get negative 9.8 meters per second squared. And it's going to fall 1.85 meters. Oh, immediately, boo, yes, why?
It should be negative.
Displacement's negative, because if you do this, what are you going to get? You're going to get a negative underneath the radical. You're going to have imaginary velocity, okay? Which is tough, okay? Especially if you get pulled over. You know how fast you're going? No? Surprise me, it's an imaginary value. Stop. Now, can we just randomly make this a negative value? Or is there a mathematical basis for it? Yeah, what's my final position? What's my initial position? 1.85. Check my math, but if I take 0 minus 1.85, I get negative 1.85. Now, I am on the test, so help me. I'm going to tell you all this right now. I better see those negative signs underneath that radical. Okay, that's going to be part of the test. Do you understand the complexity of this problem? Okay? This, writing the equation, then a miracle happening, and oh, here's my velocity. No, Mr. Texas, that is not going to cut it. Okay? I want to see the numbers, and Topher Knizzo, I would really like to see some units. I know that's against your religion, but that might be handy. So, this is what I'm going to expect to see. So, somebody crunch the numbers and let me know what you get. 6 point what? 6 point what? 6.02. Everybody cool with that answer?
No. Negative.
Yes. Which direction is the ball going? Down. What's the square root of 4? 2 or negative 2. What do you have to do? You got to choose the negative root. Okay? Calculator lied to you. Did not do you a solid. Okay? Got to choose that negative root. Okay. Now at this point on our extreme velocity time graph, we know it's going to hit at negative 6.02 meters per second. Okay, that's the number. Now, let's think this through. When I find the velocity when it leaves, okay, now I have a benchmark, negative 6.02. Now I have a benchmark. So the velocity when it leaves, is that going to be bigger or smaller than 6.02?
Smaller.
Smaller, because it only goes to a height of 1 meter. So now I know when I find my new velocity, it can't be bigger than 6.02. So that at least gives me a reference to go from, okay? Gives me an idea. All right, so on the way up, oh, for the love of, on the way up, what's my initial velocity going to be? It's not going to go very high if my initial velocity is 0.
6.02.
Oh, how high did that go? Not very. Okay. Jump, boy, come on. Okay. Do you know your initial velocity?
No.
No, that's your unknown. That's what you don't know. Okay. It's a trick question.
LOL.
What's the final velocity going to be? 0. Cooper, what's the acceleration?
Negative 9.8.
Oh, fantastic. Okay. Why doesn't the acceleration become positive? It's going up. Yeah, gravity's still trying to keep you down, right? The acceleration does not switch signs. The velocity does, but not the acceleration.
Agreed.
What else do you know? It's kind of a Colorado thing. You know how high it goes, right? So, it's a subtle thing. So, I was talking about the mountains, by the way. So it goes to a height of, I could never teach physics in Colorado, I'm telling you that right now. You'd be like, dude, no. Oh. Now, is the distance on the way up a positive or negative value?
Positive.
Positive. Because when it leaves, what's the initial position? What's the final position? 1. Take 1 minus 0, check my math, you get 1. Preston,
Yeah,
what equation am I going to use to find the final, or find the initial velocity?
it's gonna be that equation.
I am. Now, here's the tricky part. Here's the tricky part. What do you have to solve that equation for? You got to solve it for V naught. Now we're searching for V naught. Okay, to V naught or not to V naught. In this case, we V naught. So this is like Shakespeare meets Newton. So we have V squared minus, and then what? Square root of all that.
Plus or minus.
Now, here's the tricky part. What's my final velocity going to be? 0. Okay, it's important that you put that in there, and here's why. Because we're going to have 0 squared minus 2 times negative 9.8 meters per second squared times 1 meter. So here's the significance of this. So now I have 0 squared minus a negative number. So since I'm subtracting a negative number, guess what? Then I get a positive value underneath that radical. Okay? And yes, I'm going to look to make sure that you have this negative sign and you have 0 squared minus that. Okay? That's going to be some of the points on this problem. Did you work it with the correct signs? Now, what do you get out of this?
4.43.
What'd you get?
4.43 meters per second.
4.43 meters per second. Positive or negative?
Positive.
Now, does that match with what we predicted?
Yeah.
Yes, because we said it should be a positive value, but less than
6.02.
6.02, and that's what we got. Okay? So it's cool at this point. So at this point up here, now it's going to leave at 4.43 meters per second. Okay? Now, here's the most important transition in this entire problem. Okay? You've got to stay with me through this transition. We need to find the change in momentum of the ball when it's in contact with the ground. Not when it's falling, not when it's going up, when it's in contact with the ground. So we're going to use change in momentum equals mass times V minus V naught. Okay? Now, here's the trickiest part, which is not the mass, by the way. That's 0.254 kilograms. That isn't the tricky part. When it's in contact with the ground, is the negative 6.02 that we found, is that negative 6.02, go away, is that negative 6.02 my V or my V naught? V naught. Because that's how fast it's going in that transition. So the 4.43 is my V. So when I do this change in momentum, my V is going to be the 4.43 minus, wait for it, a negative 6.02 meters per second. Now, this is the tricky part of this. Okay? When you found V here, that last step, when you found that V naught here, when you found that velocity here, that became V, what? Here, okay? And when you found the final velocity when it hit the ground, that became the V naught here. So you have to like cross these over. So when you're going to use Preston's, that equation, you're going to use that twice. But the V that you find becomes the V naught when it hits the ground, and the V naught that you find when it leaves the ground becomes the V. Okay? So you got just mull that over. Okay? You got to think through this process going, okay, great. Hey, I'm finding the change in momentum. But you're finding the change in momentum when it's in contact with ground. Not while it's falling, not while the ball is going up, when it's in contact with the ground. So V becomes V naught becomes V. Okay? Now, what do you get out of this calculation?
2.7.
What'd you get?
2.65.
What? 2.65? What did you say?
I didn't say anything.
Okay?
What? What is so funny?
I don't know.
Everybody cool with that answer?
Go with that.
Okay? Have units of Newton seconds. This is going to be important. Now we have to change the momentum. Now we know how long the ball was in contact with the earth. Okay? Now, do we have enough information to calculate the force on the ball? Yes. Now, are we going to use the time that it falls or the time that it's in contact with the ground? Just the time that it's in contact with the ground. That's all we're going to use. And I gave you that time, whatever that was, 1.28 times 10 to the minus second. So force times time, oddly enough, equals change in momentum. So I gave you the time, right? So I'm going to take 2.65 Newton seconds and divide that by whatever it is, 1.28 times 10 to the minus second seconds. Seconds cancel out. You get newtons, which is what force is measured in. So what do you get? 207. Now, does it make sense that you have a positive force acting on the ball? Well, which direction does the ball bounce?
So yeah, it doesn't make sense.
Could your force be a negative value?
No.
No, I'm not going to make the ball bounce up in the air by pushing down on it.
Yeah. Okay.
Okay?
Yeah.
Right?
Right.
Okay? So my force has to be a positive value. Now, ball hit the earth. That was a change in momentum of the ball. When the ball hits the earth, what's the change in momentum of the earth?
Negative 207.
No, change in momentum,
Negative 2.65 Newton seconds.
right? So, if the change in momentum of the ball is, what was it, 2.65 Newton seconds, because momentum has to be conserved, what's the change in momentum of the earth?
Negative 2.65.
Negative 2.65 Newton seconds. Because momentum has to be conserved, right? Changes in momentum are equal and opposite. Now, think about this. Let's look at Newton's third law. That was the force exerted on the ball. Okay? Upward, 207 newtons. What's the force that the ball exerts on the earth?
Negative 207.
Negative 207 newtons. Newton's third law. It isn't Newton's suggestions. It isn't Newton's, just on test day. Okay? Or just if the forces are the same. Or if Burkamp asks us about it, otherwise it's just true. Okay? It's a law. Okay? It isn't just kind of. Okay? It's a law. So, the force on the ball was 207. So by Newton's third law, the force on the earth is negative 207 newtons. Okay? Now, can we, Topher Canizo, can we find the acceleration of the ball?
Yes.
How?
F equals ma.
Fantastic. You know the force on the ball.
Yep.
You know the mass of the ball.
Yes.
Find the acceleration. So, the force on the ball, we said was 207 newtons. So if I take 207 newtons and divide that by 0.254 kilograms, what do you get? What'd you get? 816. Positive or negative? Hopefully positive. Okay? Now, how does that acceleration fit way back up here on that velocity time graph?
Acceleration.
Oh, that's the acceleration of the ball when it's in contact with the ground. Notice that that's a big positive number. So that positive acceleration is making it slow down when it comes in contact with it, and then that same acceleration is making it speed up. So notice that this is positive the entire time. So that positive acceleration is doing two things.
Can I have Sam read sheet from you?
Yes. Just don't bring him back.
Yeah, we don't.
Yeah, Sam, sorry. you're not. So that's going to be the slope of the line during that interval. Now we have one thing left to do, and one thing left only.
Is it small? We have this corner.
One thing left.
Sorry.
I need to find the acceleration of the Earth. Is the acceleration of the Earth also going to be negative 816 meters per second squared?
No.
No, thank God. Okay? Because if that was the acceleration of the Earth, when that ball bounced up like this, what would the Earth do? The Earth would accelerate out from underneath us. Okay? Friday nights during basketball season, the world would be a train wreck. Every time a kid bounces the ball, boom, the Earth would accelerate out from underneath us. Okay? So, here's the million-dollar question. When you have a collision, are the changes in momentum equal and opposite? Yes. No exceptions. Are the forces equal and opposite? Yes. No exceptions. Do not overthink this. Do not overthink this, Morales Chapman. Do not overthink this. There's no exceptions. Okay? Forces equal and opposite. Changes in momentum equal and opposite. Nothing to think about. It's automatic. What about the acceleration? No. Could we calculate the acceleration of the Earth?
Yeah.
Do you think it's going to be a very big number? No, thank God. Okay? So, to find the acceleration of the Earth, somebody take negative 207 newtons and divide that by the mass of the Earth.
Negative 3.46.
What'd you get?
Negative 3.46 times 10 to the negative 23rd.
Times 10 to the negative 23rd meters per second squared. So every time, like, you jump up in the air, you just made the Earth accelerate. Okay? It's cool. It's like, put that on your college application. What do? I make the Earth accelerate every time I jump. Cool.
No, that's what I was thinking. What if we
Yeah, you can get into that argument, like, what if everybody jumps at the same time? Best, you might create a small earthquake, but, okay. So I promise you, listen to me, I promise you, this problem is gonna be on the test.
so torn.
The only thing I can do is change the numbers. I can change the two heights, I can change the mass, I can change the time. That's it. It's the only thing I can do. So if you really want to make sure, and this problem is going to be worth more points than anything else. So if you want to make sure that you get this right between now and next Wednesday, every day work this problem, okay? Change the numbers, create a group chat. Hey, somebody today, You know, somebody make up the numbers, work the problem. Tomorrow, somebody else make up the numbers, work the problem, okay? You know, I'm not, in case you all haven't figured this out, when I tell you what's gonna be on the test, guess what? It's on the test. It isn't like I walk in and the tests are there and go, oh man, I didn't tell them that was gonna be on the test. Oh, I feel bad. Okay, no, okay? When I tell you it's gonna be on the test, it's gonna be on the test. Okay, so, stop that. And let me fire, I gotta.
Which has been protecting families and businesses for generations. Have you heard from the Quiet Company? Northwestern Mutual Life.
And by the Corporation for Public Broadcasting and viewers like you.
Every day, more than 100 people die in car accidents. This one is in Memphis, Tennessee. In one dreadful moment, 3 lives have been shattered. 2 of these victims will not survive the trip to the hospital. In the last 100 years, more Americans have died in car crashes than in all the wars the United States has ever fought.
Now, let's just let that soak in. Okay, the last 100 years, more Americans have died in car crashes than World War I, World War II, Civil War, Korean conflict, yet all those others. We've lost more Americans' lives to car crashes than anything else. So, and here's a simple solution. You reduce the overall speed limit on everywhere to 30 miles an hour. Here's the deal. You cannot build a car that goes faster than 30 miles an hour. You are going to greatly reduce the number of deaths. But what's going to happen if you did that? People would riot. Okay? They would. They would, no, I want to drive 70 miles an hour down a highway. So here's basically the calculus that we have made as a society. We have said we're willing to accept a certain number of deaths in automobiles so we can drive fast. Okay? That's the calculus that we've made. So it used to be, for years, the speed limit was 55. Because there was an oil embargo and it was a whole long story. Because cars get better gas mileage when they drive 55. So they lowered the speed limit to 55 to improve the overall mileage of cars. And then, once that oil price is passed, people said, hey, let's raise the speed limit back up to like 70. And the engineers are going to go, if you do this, you're going to have more people die in accidents. The faster you go, the more kinetic energy there is, the worse things are going to happen. And basically everybody said, we're cool with it. We're good. Let's go ahead and bump it up to 70. It's like, okay. But that's the calculus that we have decided as a society, that we are willing to accept a certain number of deaths and car accidents because we want to drive fast. I'm not saying it's right or wrong, I'm just telling you that's the calculus that we decided.
Is there a way to make these devastating accidents survivable? This is Germany's infamous highway system, the Autobahn. For long stretches, there is no speed limit. Some cars cruise at 100 miles an hour and faster. Occasionally, German police cameras monitor the roads. Most of the time, traffic flows in predictable patterns. But recently, the cameras recorded a shocking event. As shown on the small screen in the lower right, a Mercedes in the oncoming lane is about to round the far corner, traveling almost 150 miles an hour.
So look at the top right corner.
Playing back the tape, the police were able to see exactly what happened.
Not enough friction.
The car was going too fast to make the turn. It grazed the guardrail on the right, and the driver lost control.
You got a lot of momentum.
After sliding 400 feet upside down, the car comes to a stop on the embankment, and the removable top flies off. Clearly, a horrifying accident. But what happens next is almost unbelievable. The driver climbs out, not only alive, but uninjured.
Shaken.
A lucky man, certainly, but he also owes a large debt of gratitude to modern engineering.
The driver in this car was very lucky because he survived a very severe accident with a special safety feature, which is in this model. As you can see, it's a rollover bar, and this rollover bar is very stiff and helps to guarantee a certain survival space.
As the car tilts, sensors trigger the rollover bar to pop up, creating a space between the driver's head and the pavement.
If you're wearing
Wearing a
seatbelt.
seatbelt is crucial to keep the occupant inside.
And you're not very tall.
Before the rollover bar was introduced in 1986, this kind of accident was unsurvivable. In the last 30 years, science and engineering have helped create much safer cars. Today, no new model hits the showroom without being rammed into walls, barriers, and other automobiles to comply with international standards of safety. But it wasn't always this way. Automobile safety came slowly and at the expense of millions of lives. This is a 1929 Chevrolet, crash tested using today's standards.
Out we go.
Well, cars of that era were rickety affairs. They were sheet metal nailed and screwed onto wooden frames, and so they were very insubstantial, and when they got into a serious crash, they pretty much disintegrated.
Survival in one of these motorized coffins was due mostly to luck and the fact that cars were slow and scarce. The automobile age began in Germany. Powered by a combustion engine, the first car was built by Carl Benz in 1886. For years, the automobile was considered a toy in Europe, meant only for the very rich. It was an entirely different story in America. Soon after the turn of the century, low-cost automobiles went on the market, and Americans bought them in staggering numbers, even if the roads weren't always ready for them. As the number of cars increased, so did accidents. By the early 1920s, more than 500,000 people had died in collisions. Yet nobody blamed the automobile. Accidents were considered an act of God, or a bad driver.
It was obvious to blame the driver, the human being, rather than the inanimate object, and so the automobile industry accepted that and therefore assumed that they had no responsibility for designing cars to be involved in accidents.
Automakers avoided the topic of car safety. Sales could be hurt if customers began to think of cars as dangerous machines. There was, however, one aspect of car design so lethal, everyone recognized the need to change it. Plate glass windows. A minor collision, even a small rock tossed up by a passing vehicle, could shatter a windshield, sending razor-sharp shards of glass inside. In 1910, a laboratory accident would lead to a major advance in glass safety when Eduard Benedictus, a French chemist knocked a flask on the floor. To his amazement, the bottle broke but didn't shatter, because it was coated with nitrocellulose, which had dried out, leaving an adhesive film on the inside. Benedictus didn't think much about the incident until he read of an auto accident in which a young girl's face was disfigured by flying glass. Moved by the reports, he went back to his lab. The result was a sheet of celluloid adhesive between two pieces of glass. Bonded together, they made one clear pane, the middle layer holding the lethal pieces in place. An improved form was first used in gas masks during World War I, but it took 16 years and an accident to get safety glass used in cars.
When Henry Ford was designing the Model A, one of his engineers was injured by flying glass from an accident, and he and Edsel Ford decided to offer it in all of the new Model A's, all of the Ford models.
Safety glass was considered such an important advance, car companies even advertised it.